Okay, taking our look at the calendar. Today is February 29th, happy leap day. We are going to cover something called trigonometric substitutions. This is our last integration technique of the semester. We did the basic integrals. That's a small list of things that we can actually do. U substitutions expanded that list significantly. We did partial fractions and we did integration by parts. We have one final technique, that's today's technique. So I haven't finished grading your tests yet. So here on March 2nd, where I said your grading choices due, I'm going to push that back a day. So I will hand you your graded test back on Wednesday. On Friday, I will ask you to tell me how you want me to calculate your course grade in terms of the percentages, all right? So there's information about that on the syllabus, but that's not going to be due Wednesday. It'll be due Friday. Okay, so trigonometric substitution, we got a brand new packet here, which we start on page 3. And I just want to put out there at this particular moment, you're all in a good mood after the happy leap day math discussion that we had. So don't let the misery of trig substitution alter the fact that at this moment right now, you're feeling pretty good. All right, here we go. Another new integration technique called trig substitutions. We're going to skip number 1 and jump down here to number 2. Trigonometric substitution. We can substitute trig functions to simplify integrals involving a squared plus or minus x squared. A is just a number. For example, in number 3, how much is a? If this is an a squared minus x squared, a is 3. 3 squared minus x squared. So let's see if we can try number 3. Integral of 1 over the square root of 9 minus x squared. Don't write this down, but if we were going to try maybe a u substitution, what's our natural choice for u? 9 minus x squared, not including the radical, just the stuff inside. And we take our derivative. Again, you're not writing this down, and we get negative 2x. And if you can see a little bit into the future, you recognize that this is the end of the ballgame. Because if you were to substitute, you'd end up with what? Du over negative 2x, yeah? And that negative 2x is a real problem for us because it doesn't have a partner in the top that it's going to cancel with. So we'll have x's and we'll have u's, and it didn't work. We tried. This is definitely not an integration by parts. There aren't even 2 parts in here, but again, don't write this either. But if you wanted to do parts, I guess you're putting everything inside of the u, right? Because you can't put it on the dv. And taking a derivative of this is undoubtedly going to make it worse, right? It'll become some stuff to the negative 3 halves times a negative 2x chain rule pops up, and all of a sudden the new integral is worse than the original. Okay, 0 for 2. Partial fractions was where the bottom is a polynomial, right? We try to factor the bottom. That is not a polynomial, even though we can factor 9 minus x squared, right? It's 3 minus x, 3 plus x. But it's inside of a square root, and our partial fractions technique does not account for any square roots sitting down there. So it's not that. In fact, it's not anything. We need a brand new technique. So here we go. We are going to make a strange substitution. Here it is. I'm going to let x equal 3 sine of theta. Go ahead and do write this. Okay, so you don't need to write this piece over here, but that's kind of a strange substitution. So really, I guess what I'm saying is that I'm letting theta equal the inverse sine or the arc sine of x over 3. You don't need to write that, but that's really the substitution. Like if you solve the first equation for theta, divide by the 3 and then take the inverse sine. Yes, we get that. So typically, you know, it's a u substitution. You let u equal something, right? Typically, you let u equal a piece of the original integral. I don't know where that inverse sign came from, but it certainly wasn't in the original integral, but that's not required for substitutions. You can let u equal anything you want, and we're just not calling it u. We're going to call it theta because it will represent an angle at the end of the day. So a really strange substitution. I'm writing it in this equivalent form here. I'm going to go ahead and take a derivative of this guy. Derivative of x with respect to theta. What's the derivative of 3 sine theta? 3 cosine theta. And just like for u substitutions, what did we solve for at this stage? We would solve for dx. We're still doing that. So multiply the d theta on both sides. You get 3 cosine theta d theta. Okay, now it's time to start substituting. We've done all this work. It's not clear how it's going to help us, but let's at least see what the new integral becomes when we do all our substituting. So here we go. The original integral, again, we'll call it I, is equal to integral 1 over square root of 9 minus, I'm going to put some blank parentheses squared. It used to be x squared. What am I putting instead of x? 3 sine theta. That's what I let x equal. Don't worry about where that choice came from. We'll explain it at the end. But anyway, that's our substitution. Now this is an important piece. The next thing is a dx. You need to put something that is equivalent to dx. Don't just put d theta. You might make the integral go from something that's easy to something that's impossible. What is dx equal to? 3 cosine theta d theta. So it's not clear that's any better. In fact, you could make the case it's worse, but it's equivalent, yes? Everything we've done is legal. All right, let's keep going. Equals integral. Let's see, so I'm just going to copy this guy here. I've got, I'll put the 3 cosine. Oh, it doesn't matter. I'll leave the 1 on top. Copy the 3 cosine theta d theta here. It's the stuff in the integral that we got to focus on. Sorry, the stuff in the radical that we have to focus on. 9 minus, okay, so 3 sine of theta squared turns into 9 sine squared, right? And just a reminder, if that notation is not super familiar to you, when we say sine squared, it's just an abbreviation for sine of theta, the whole thing squared. Okay, what can we factor out in the radical? 9 comes out of both of those, so let's do that. Okay, integral 1 over square root of 9 comes outside of the parentheses. And we're left with 1 minus sine squared. And then copy that 3 cosine theta d theta. Yeah, so the 9 can come outside as a 3 now, outside of that radical. Okay. Mm-hmm. Okay, so this guy's coming down here equals integral 1 over. Okay, so as we said, that square root of 9 can come outside of the radical and just become a 3. And then we're left with this 1 minus sine squared. And then everything else is just a lot of copying. Not sure if I've said this before, but I think a lot of good math practice is copying almost everything and making one small change. You would be surprised how many mistakes folks make because they're trying to do 2 things in one step. So lots of copying, a little bit annoying, but far safer than doing 2 things in one. Okay, so sure, the 3's cancel, but that's not where the money is. The money is that thing inside the radical. That thing inside the radical hopefully looks familiar. You guys know a lot of trigonometric identities from your pre-calculus days. 1 minus sine squared is cosine squared. That's what's going to make this thing work. I'll put it off over here on the side in an alternate form that might look more familiar. Sine squared of theta plus cosine squared of theta is identically 1. So subtract the cosine squared, subtract the sine squared. And all of a sudden 1 minus sine squared can change into a cosine squared. That's the key. This equals integral of 1 over 3 square root of, lots of copying, 1 minus sine squared we just said is cosine squared. And copy everything else. We will. So we'll end up using that at the end. Oftentimes you don't end up using it, but yeah. Okay, square root of cosine squared. It's cosine. All right, and that's the heart of this method, is that we did all of that work and that very strange substitution to get rid of that radical. That's what we accomplished. And hopefully the integral that we get left over is something we can handle, but we got rid of the radical. So this guy equals, what do we have? Integral 1 over 3 root cosine squared is just cosine times up there 3 cosine theta d theta. And then miraculously, lots of stuff cancels. It doesn't always happen as nicely as it will right here. All we can guarantee is that that radical is going to go away, and we cross our fingers that what's left is something manageable. So this is really just the integral of what? D theta, just 1 d theta. Okay. What is the integral of d theta? Theta plus c is good. And we're done, except we made a substitution, right? The original problem had what variable? X, and this theta is an invention of ours, so we need to go back. Just like at the end of a u substitution, you go back to the x's. So we need to figure out what theta is, and so we've got this definition up here that x is equal to 3 sine of theta. And so I told you not to copy it before, but as Dave said, this blue thing is the solution for what theta is really equal to, right? We need to figure out what theta is. So we divided both sides by 3 and then take the inverse sign. So inverse sine of x over 3. That's what we're going to put in our final answer. Okay, so our last answer here equals inverse sine of x over 3 plus c. Yes. Oftentimes it'll be like cosine of theta or some trig function of theta. It's usually not just theta. Actually, I'm not a fan of solving for theta in the first step because, as you'll see in one of the first activities, instead of solving for theta, you'll draw yourself a right triangle, and then you'll find what the final answer is without ever needing theta equals, theta by itself. So you'll see it. You're welcome to solve for theta, but that's not typical that will be the final answer. Okay, so you should have one big question at this point about where that original substitution came from, right? Out of the blue, I said, hey gang, x equals 3 sine of theta is the magic substitution. And it wasn't because I could do all this in my head and saw it to the end. It's because there's a little formula that we're going to use. Why was 3 a good number in this problem? Because of the 9. And we knew that whatever we substituted for theta was going to end up getting squared, right? This 3 sine of theta ended up getting squared, and so that allowed us to factor a 9 out of both terms. Okay, so then whatever number you see there, what do you do to figure out what goes here? Is you take the square root. Super, that's step 1. Okay, why was it that sine of theta was a good solution instead of cosine or tangent or secant? Well, when we ended up here with this 1 minus sine squared, we were able to use one of our trig identities, right? If this had been a cosine squared, could we also use that same trig identity right here? Yeah. So you could actually have done it the other way. You could have cosine there, and you get an equivalent, slightly different looking final answer, but it would be equivalent. It turns out that if you see a number minus x squared, we're just going to do sine every time. If this was a plus, we're going to do tangent. You'll see why tangent is the right tool when you do the activity. Dave? It's just an arbitrary choice. Yeah, you could do cosine and it's the same amount of work. Yeah. Okay, so here's some trig.
Plus, it's tangent. If it's negative, it's cosine over.
Sine or cosine. I'm just going to say we'll do sine every time. But yeah, it's written on the next page. If you see a squared plus x squared, you do a tangent theta. Okay? Trevor. It's a good question. So what if you had something like this? So first, sine, cosine, or tangent, what are we saying in this case? We're saying tangent. Okay, so tangent theta. What's the magic number that goes in the front? Square root of 5. Yeah, no problem. Okay. All right. So take a gander at the general suggestions there. Your first practice problem is here. And just recognize that trig substitutions are really hard. Okay, I'll walk around and help.